Second part of this module is optical fibers. Now we are going to learn about this optical fibers. What is meant by an optical fiber? Optical fibers are essentially light guides which are used in optical communications as waveguides. They are transparent dielectrics and are able to guide visible and infrared light over very long distances. Here we can see the schematic diagram of the optical fiber, in which it consists of two parts. The inner part is called core, outer part is called cladding. So the inner part is made up of glass or plastic, and the outer part is also, which is concentric cylinder surrounding the core. It is also made up of similar material but of lesser refractive index. And we can see the material continuity between core and cladding. So the cladding is enclosed in a polyurethane jacket which provides or protects the fiber from chemical reactions with respect to surroundings and also against aberration and crushing. So such a type of some hundreds of optical fibers which are grouped together, combined together, form a cable. A cable may consist of one to several hundred of such fibers. So the next diagram shows the fiber wave propagation. As we know that the waveguide is a tubular structure in which energy of some sort could be guided in the form of waves. Since light waves can be guided through a fiber, it is called as a light guide. It is also called as fiber waveguide or fiber light guide. So, and what is the basic principle that the optical fiber works? It is nothing but TIR. What is this TIR? It is total internal reflection. So what is meant by total internal reflection? Let us try to understand with the help of this diagram. We are considering a boundary which is separating two different medias having a refractive index of N1 and N2. And we are considering a ray, light ray AO, which is of refractive index N1. Let this XX dash be the boundary that is separating the two media, and this AO, when it is light ray, makes an angle theta 1 with the normal in the medium of refractive index N1. As this ray enters into the medium, it gets refracted of refractive index 2 N2. It bends away from the normal since N1 is greater than N2. If theta 2 is greater than theta 1, let us say that is angle made by the refracted ray with the normal is greater than theta 1. If theta 1 is increased, if the angle of incidence is equal to critical angle, then the refracted ray grazes along the boundary. If the angle of incidence is greater than the critical angle, then the entire ray reflected back into the same medium. So that is what we should understand, that this condition is called as a total internal reflection. So, and here we have given that what is the condition for the refraction from the Snell's law is N1 sin theta 1 is equal to N2 sin theta 2. When theta 1 is equal to theta c, theta 2 will be equal to 90 degrees. So N1 sin theta c is equal to N2, or theta c is sin inverse of N2 by N1. So what is the importance of this total internal reflection? Let us try to understand. So it is not just some similar one kind of reflections. It has a very special importance, and it is unique from the other kinds of reflections. The difference is when you consider a normal mirror, the surface of a mirror, when the light is incident during its reflection, certain amount of energy will be lost due to absorption, whatever the best quality of reflection it happens to be. But in the case of total internal reflection, there is absolutely no absorption of energy at the reflecting surface. The entire incident energy is returned along the reflected light. The entire incident energy is reflected back into the same medium. So that is why it is called as total internal reflection. So because of such an extraordinary facility of absolutely no loss of energy during reflection, the optical fibers are able to sustain their signal transmission without any loss over very long distances. So if at all any small amount of loss occurs also during reflection, the fiber optic communication will be very highly not possible. So that is the importance of total internal reflection. So next we are going to understand about the numerical aperture, that is nothing but ray propagation in the optical fiber. So let us consider this special case of an array which suffers critical incidence at the core and cladding. We are considering an optical fiber which is having the core and cladding, and the refractive indices of surroundings is N0, core is N1, and core cladding is N2. So the ray to begin with along AO, it is entering into the core at an angle theta naught to the fiber axis. Then it gets refracted by an angle theta 1 and proceeds to fall at a critical angle of incidence at point P, which is equal to 90 minus theta 1 on the interface between core and cladding. Since we are considering the incidence as in critical angle of incidence, the refracted ray graces along the path BC. Now we can say that any ray that enters into the core at an angle of incidence theta naught, which is less than theta naught, angle of refraction is less than theta 1, then 90 minus theta 1 will be greater than the critical angle. So it becomes the critical angle of incidence when it undergoes the total internal reflection. On the other hand, if theta naught is greater than theta is greater than theta naught, then it is greater than theta 1, then 90 minus theta 1 will be less than the critical angle of incidence. At such incidence, the refracted ray enters into the cladding region and travels along the thickness of the cladding and emerges into the surroundings. So when it is equal, it grazes. When it is greater than the critical angle of incidence, it undergoes total internal reflection, and when it is 90 minus theta 1 is less than critical angle, it enters into the cladding and emerges out. So these are the three possibilities. Now if this light rays rotate around the fiber axis, keeping this theta naught as constant, you can observe it sweeps a conical surface. We can therefore say that if a beam converges at a wide angle into the core, then those rays which are funneled into the fiber, they will only undergo total internal reflection within the confined propagation, and rest of the rays will emerge from the sides of the fiber. So this theta naught, I am calling it as acceptance angle. Sign of the acceptance angle is called numerical aperture. Let us now try to understand the derivation part of this numerical aperture, and we will obtain the condition for the ray propagation. So for this, N0, N1, N2, as we know, these are the refractive indices of the core cladding and surrounding core cladding, and you are applying the Snell's law at point A, then N0 sin theta naught is equal to N1 sin theta 1. Similarly, at point B, the angle of incidence after applying it is equal to 90 minus theta 1. So when N1 minus N1 sin 90 minus theta 1 is equal to sin 90 into N2. Therefore, N1 cos theta 1 is N2. Therefore, we are getting cos theta 1 is N2 by N1. Similarly, we can also write sin theta naught substituting in the equation 1. You can get sin theta naught is N1 by N0 into sin theta 1. That is nothing but N1 by N0 into root of 1 minus cos square theta 1. So N1 by N0 into 1 minus, we are substituting the value from using the above equation, N2 square by N1 square. So that is nothing but N1 by N0 into root of N1 square minus N2 square by N1. So that N1 will get cancelled, and we are left out with this expression sin theta naught is equal to root of N1 square minus N2 square by N0. So this is the expression for the numerical aperture. If N0 is equal to 1, then we are getting Na is equal to root of N1 square minus N2 square. So the condition for the ray propagation is always theta should be less than theta naught, or sin theta is less than sin theta naught, or less than numerical aperture. This is the expression for the numerical aperture. As we know from this, we can find out the relation between Na and the fractional index change, which can be defined as the ratio between the change in the refractive index of core and cladding to the refractive index of the core. So delta is equal to N1 minus N2 by N1. Cross multiplication, you are getting N1 minus N2 is equal to delta N1. And we are trying to put the relation between Na and delta. Substituting, you can write Na is equal to S in the form of A square minus B square, which is nothing but A plus B into A minus B. So you will get root of N1 plus N2 into delta N1. So that it is nothing but N1 square root of 2 delta. Therefore Na is equal to N1 times root of 2 delta. So this is the expression for the numerical aperture and relation between fractional index change and the numerical aperture.